Hey everyone, thanks for coming to our fourth workshop in the advanced track. Today we'll be talking a bit more about convolutional neural networks, so part two. Again, hope you guys are glad to be back in person or back at UCLA, and hopefully we can maybe be back in person too for these workshops. Again, the feedback form with the link to slides in it is right here, tinyurl.com/atrack4-w22. That's feedback. And if you haven't joined the Discord by now, what are you doing? But also join the Discord now, so you can stay up to date on all the stuff about this track. Awesome. Okay, two quick announcements. First one is that so ACM AI Events is holding an event called AI Labs, the modern applications of AI. And so this is going to be a really cool, I guess, panel plus talk about like some modern applications of AI, as it says. It is this Wednesday in Engineering 4, room 57-124. I don't know exactly where that room is, but I know where Engineering 4 is. You can probably look it up. And it's from 6 to 7 p.m. So if you're interested in that, definitely feel free to go ahead and check that out. Additionally, there's a UCL climate hackathon going on. And so if you're interested in like the intersection of climate change and AI, two pretty big issues and I guess problem spaces, check out this climate-based focused hackathon called Climate Hack AI. It's basically a central problem, and like you and your team can work together to try to like create the best model possible. And so some of the tools we talked about in this course and this talk actually can help you out with this challenge. And so if you're interested in that, check it out. And then one thing I wanted to announce as well is that we will be putting like a poll on the Discord about if people want to go back in person or not. Personally, we prefer to, but if everyone's not wanting, or like if people don't want to, obviously we want you all to attend, so we'll stay online in that case. But please check the Discord this week to make sure that you're like respond to that poll if you want in-person workshops the rest of this quarter or online workshops for this quarter. Okay, cool. So with that out of the way, you can go on to today's content. So last week we like started going into convolutional networks. We talked about different layers in them, as well as what they did. And so today we're going to go into a bit more detail about some hyperparameters and as well as something called stochastic gradient descent, which is really important for training the model. We'll also talk about something called dropout regularization, which is a pretty cool way to make your model not overfit. Next we're talking about a couple more advanced networks that use convolutional networks. So Inception, Resnet, and UNet. And then we'll go into two pretty important concepts for training pretty big neural networks called pre-training and transfer learning. They're both important steps or important ways to train models that can improve performance. Okay, so in the past, we talked about gradient descent, and we talked about the fact that like you could think of your cost function, at least in 2D, for like a one-dimensional cost function. So you have cost on the y, and you have one weight, and that weight is on the x. And so basically, you can see that if you change your weight around, you can basically lower or increase your cost. And so the way gradient descent usually works, that we're going towards the bottom. We're basically following the opposite of the gradient. So we're going down the direction of steepest descent, and through that we're getting to a minimum of some sort. So we're going down a valley in a sense. So from here on the ball, we're going down to this valley. However, there's the problem of the fact that cost functions aren't usually like so simple, where there's only one global minimum and no other minimums. So as we see here, there's cases where you can have a local minimum, which is like a minimum relative to the things around it. So this point right here, its cost is relatively low, like it's the minimum cost relative to the area around it. But there's obviously a way better cost function over here. But with regular gradient descent, we're not going to get there, because why would we increase the cost this way instead of decreasing the cost this way? And so we wouldn't do that with typical gradient descent. And so with that, we can move into actually what stochastic gradient descent does. And so the first part for stochastic gradient descent is going to be hyperparameters. And so again, remember the hyperparameters are used, are chosen by us, the users. So we get to tell the model what data point or like what values we're going to use for these hyperparameters. And so with this, we get our control of the model. So we can like basically change the way it's training as well as how to, I guess, like the model trains in general. So some examples include learning rate. So remember that learning rate is like we get to choose it, and basically that tells the model how fast to go down the gradient for gradient descent. Mini batch size, which basically tells you how many, I guess, data points to train on before computing backpropagation, which we discussed last week. And things like number of hidden layers in the network. So basically, number of layers in between the input and output layers. And so these hyperparameters allow us to change the format of the model as well as how it trains. So batch size, going into more detail about batch size, I just mentioned it earlier. So batch size is basically number of training samples used for one backpropagation cycle. And so you can think of it basically as if we had a batch size of 10, right? And going back to our example last week about like handwritten digits, basically we'd give our model 10 different images of digits, and then we figure out the cost of each of them, the loss function on each of them, and we sum that up. Then we take the backprop of all of those 10, I guess 10 data points. So basically, we're batching our data points in a certain section. And so you can see it on the right. Quick example of that. We can see basically we have these containers for baby food, and basically we're breaking up a bunch of food into a bunch of small batches. And so yeah, as I said here, you calculate the cost over those n samples and backpropagate with the cost function. And then mini batch size is a portion of the current batch size. It's a hyperparameter we choose. And so batch size is a pretty important hyperparameter that we get to choose. And so when you have smaller batch sizes in general, you're going to be backpropagating more, right? You're going to be updating your weights more, which makes it learn faster, but it can be more volatile. So the reason that is because you're going to train faster is because you're changing your weights so often, right? So you're going to get better over time. However, if you have some outlier data, you might train in the wrong direction. That might lead to volatility. And so you can see here in the diagram over here that like over time, basically these are different batch sizes, and the small ones like 4 and 8 have like these really big peaks. I'm pretty sure this is like either loss or accuracy. Probably accuracy actually. So you can see that the accuracy has like these really big values due to volatility. While like you can see like something like 256, for example, generally grows over this I guess logarithmic curve that's like pretty stable. So you learn way faster in the small batch sizes, but you learn more consistently in the big batch sizes. And so going back to, I guess, the whole problem in general, in supervised learning, which we're doing right here, we're going to be passing in data points. So for example, we're passing in like in the bottom corner, we're passing in like an image, which has like an array of pixels that are like a handwritten digit, for example, right? And then that's also paired with the actual label or expected output. And so the label for this case is 4 because we know for forehand this is a 4. And so again, remember our data set is a bunch of pairings of input data as well as labels. And so we have we can use the labels to train our model over time. And so continuing the MNIST examples, MNIST is a data set of digits. And so MNIST has 70K pairings. And so the way they break that up is that they have 60K for training, so basically making the model better, and 10K for testing, basically to figure out how well the model's doing at certain times. So we improve our weights with 60K pairings. Then we figure out how accurate we are in general with the remaining 10K pairings in our testing set. Any questions so far about this background, these background details? All right. So building off that, you might wonder, we have 70K data points, right? Why do we split it into 60 and 10? Like we could be using those 10K for more training, right? And so the reason for that is, I guess building off what I said last second ago, is to have like a set of data that our model has not seen before. And so we're going to use that data to figure out if our model has generalized to data it hasn't seen before at all. And so an example that I think I've given before, but I'll talk about again, is, for example, if like when you're a young kid, right, your parents are teaching you what different animals are, like looking at, like giving a picture of an animal, what's the animal, right? So let's say your parents have only shown you pictures of cats, right? And so you see a bunch of colors of cats and they're like, that's a cat, that's a cat, that's a cat. Everything's a cat, right? And then they show you like a dog. And so you think, hey, that has fur, that has ears, that has a tail. That's a cat too. And so that's like a problem with only learning on having a big training set, is because only having a training set, because you're basically memorizing the data, and then because you haven't seen or generalized to like a bunch of data yet, you have a higher error on data points you haven't seen before. And so the point of testing data is basically to see, has our model, like, can our model perform well on data it hasn't seen before, because it hasn't like learned the patterns of that data. Yeah. And so you can see here, like, for example, if your training that error is really low, which is a good thing, but your testing error is really high, but the training error just doesn't really matter because your model's not going to do well in the real world, basically. And so to build on that even more, for example, sometimes like a small section of training samples, we basically like we hold it back for a validation set. And so we basically use that to help us choose, I guess, hyperparameters for our model. And so a question I will ask you all is, why would we want to separate validation and test data? Even guesses are fine. Or if you have any questions as well, feel free to ask questions about this. To make sure tests are performed optimally. So what do you mean by optimally? Is it for making sure that we can eventually generalize? I guess kind of. I mean, like, yeah, it's like a good chunk of the way there. I'll just say it's a good chunk of the way there. So yeah, it's basically like, remember again that like, okay, we want to choose hyperparameters in the validation set. So since we're using them to select it, it wouldn't make sense to use them to test. Yeah, exactly. And so like, if we're like choosing hyperparameter using our model, or using that part of the data set, we don't want to test in the data set too, because technically it's that part of the data, the validation part of the data, is helping us make our model better, right? And so we want to see data we haven't seen before. And so that's why we don't put validation and test as the same thing. So yeah, those are all great answers. All right, and so building on even more, so we have an idea of what a batch is, right? And so what stochastic gradient descent basically does is basically, instead of doing like a huge gradient, I guess a huge backup over all our batches, we're going to break it up batch by batch. And so basically for one batch, we might have like 5, or we might have like a batch of 10, right? And so we'd feed forward 10 inputs. And so we basically run our model on 10 inputs. With that, we would calculate the loss of those, I guess, outputs, as well as with that we can calculate the weight and bias partials. And so with that, we can basically figure out how much we need to add or how much we need to subtract from our weights to backprop. And then after we do that for all 10 of our data points, we can take the average of like these weight and bias partials and then update the weights and biases using the same update formula we used before, but with the average partial. So the new weight is equal to the old weight minus learning rate times partial derivative. And so that's one batch. And then one epoch, it's a new term. One epoch basically means like, so given like we have n samples or n total samples in our data set, and we have m samples per batch, we're basically going to essentially run all our data points, but in small batches. And so once we run all our data points, so a certain number of batches, we will finish that epoch, and then we'll go on to the next epoch or stop, depending on what we want to do. And so basically, main innovation here is that we're making updates in batch sizes instead of one by one. And so that's the main important thing to take away here. Okay, dokes. So some discussion. So question one that I want you guys all to think about for a bit is to provide two examples, not really a question, this is actually provide an example question, but same thing. Provide two examples of hyperparameters that you might want to change in your network or make small tweaks to, and the implications of like those that each hyperparameter has on how quickly and efficiently the network can run. So I know it's a 2 here, but feel free to put 1, put 3, as many examples as you can or as you want. Okay, batch size, yeah, learning rate, size of test and training data, great examples. And so do you or anyone else want to add like what the implications or like what the effects of changing that parameter has on model learning, I guess, or like models learning like performance? Any one of them or all of them. Those are great examples though. Yeah, those are all hyperparameters that we will tweak. Cool. So changing batch size affects how much backpropagation affects the network, right? Yeah, I guess so. You can think of it basically as, yeah, so a big batch size basically means that you'll be averaging over a bunch of data points at once and then backpropping. So you'll make probably smaller changes, but they'll be like less volatile because of the fact that like you've seen a lot of data. And so that will help out. While making it really small, on the contrary, basically means that you're looking at like a very few data points and then adding their changes to the or their and then adding their like partials to the weights. And so as a result, you've only seen a few data points, and so you might make more drastic changes to the weights, which might I guess like make it more volatile because you might accidentally increase or decrease costs as a result. So yeah, great example and great explanation too. All right, I like that one. All right, question 2. So we talked about MNIST a bit, and so let's build off of that. And so let's say we're performing SGD, so stochastic gradient descent, on our network for the MNIST problem. And so our batch size is 10 samples, our training set has 60K images, and our test set has 10K images. And we wish to train over 40 epochs. And so first part I want to ask is how many images are used in each gradient approximation? And by the way, gradient approximation is similar to each backpropagation cycle. You can think of it that way too. Any thoughts? Isn't it just 60K over 40 for A? So remember, I guess, oh yeah, try, yeah. Exactly, as Preetham said, you want to explain how you got that too as well. 1500, also I see Gary's 1500. Okay. So I will add one hint in saying that, remember that like each gradient approximation, I'm basically meaning like, or we basically mean like how many images are used at each backprop cycle, I guess, in this sense. So like how many images are used to like to average out the, I guess, the gradients and then backprop that through. Kind of weirdly worded, but that's how it is. Any thoughts? Let's see. Or questions too, if you have any questions about how, like, what's confusing. Yeah. Yeah, it's basically saying that's exactly it. So basically, I guess this question is basically a weirdly like, it's just trying to get you to understand the real, like, I guess, definition of batch size. And so yeah, this basically means like we're asking you right here, like what batch size is. And I guess the way you think about it is basically every 10 samples or every batch, we're going to take all our accumulated partials, averaged amount, and then use that to backpropagate or do gradients, do gradient descent on. If you guys' question was what does 10 batch samples per batch mean, it just means like, yeah, we have 10 samples and we backprop on it. So yeah, hopefully that clears it up. If that was either I was not sure if that's the answer or a question, but yeah. Yeah, I think that question's a bit interestingly worded. I'll give you that, but hopefully it's clear that we're basically wanting to see what the, I guess, batch size is there. So moving on to part B. Now that we know what batch size is, and we gave them that here, how many times is the network going to update its weights and biases in total over all 40 epochs? $6,000. 6,000. So how did you get 6,000? $60K divided by 10. Yeah, but remember we're doing 40 epochs. So yes, 60K divided by 10 would be doing, I guess, like that would be, so going back to last or 2 slides ago, remember that if we have 60K images or 60K training samples and our batch size is 10, one epoch is going to be running, I guess, 60K divided by 10 batches in a sense. So yeah, basically multiplying 6K by 40 is, yeah, 200 or 24,000, I think. Is that right? Maybe I added extra zero. Yeah, X add X is 0. Yeah, cool. So basically what we're doing here is basically figuring out, so each epoch is going to be 60K images, but we're only backpropagating, we're only backpropping every 10 samples, right? So basically as a result, we're performing 6,000 backpropagations because every 10 images we're backpropping. And so that's 6K backprops for one epoch. Now we're running 40 epochs, so times 40 is 240,000. So wow, that's a lot, but nice calculations. All right, next part is feed forward. So how many times will this network feed forward in training? I guess
2,400,000.
2,400,000. Yeah, that should be right. Because it's just like, yeah, I'm not dividing by 10 in this case. And then how many times will we backpropagate in training? Kind of a tricky question, I guess. Yeah, it's actually just B. Trick question. But yeah, it's just B. Remember that when we're updating our weights, we're doing backprop in this case. And so, yeah, exactly. So the main thing to take away from this slide is basically each epoch is basically performing a bunch of batches for over all images. And so if we perform a bunch of epochs, we're turning over all our images multiple times. Cool. So I guess this is a thing. This problem is more about considering two different models. And so let's say we have two models with randomly initialized weights and different hyperparameters. So the main thing here is that they haven't been trained yet, but we're starting them off with different hyperparameters. And so model 1 has a learning rate of 0.01, a batch has a 40, and trains over 200 epochs, while model 2 has 10 times learning rate, 1/8 the batch size, and trains over 1,000 epochs. And so which do you think will achieve better training accuracy and testing accuracy? Or just general, which one do you think will be better overall? What does learning rate represent again? Yeah, so learning rate is basically, I guess, a hyperparameter that you choose. And so it tells you how much to update your existing weights by. So if you have like a weight W and you calculate the partial derivative of that most of the cost, so you calculate how much that weight impacts the cost. But basically, the way to get the weight for next iteration is basically the new weight equals the old weight minus learning rate times the partial derivative. So basically, how much the weight impacts it. So basically, learning rate in this case would basically tell you how fast do you want to like go down the cost gradient, or more simply, I guess, basically how much do you want to like trust your current back propagation? So like how much do you want to, I guess, change your weights depending on what the like gradient tells you to do? Like how much you weight your gradient by for updating weights, if that makes sense. And so like basically a high learning rate basically means you'll be going down that cost function really fast, but low learning rate means you'll be going slower but more methodically. So yeah. So any general thoughts on this question? Just like, which model would you rather have, for example? Let's start there. It's like, which model would you rather use? Or like have in general? The first? So why would you want to have the first one? Because even though there was epochs, it would be more accurate. Yeah, I would probably agree with you. Because at a certain point, adding more epochs in general, that doesn't really add too much performance. In actuality, at some point, adding more epochs make your model worse. And so that's a good point to add. And so in general, model 1 has bigger batch size, which is good for less volatility. And we're training over a lot of epochs, so we're going to get to our optimal accuracy at some point. So like number of time doesn't matter. And having a smaller learning rate is usually better, as long as it's not too small, because we don't want volatility in learning as well. And so in general, model 1 preferred, and model 2, while it might get you better results faster, it might not get to that amazing peak model that you might get from model 1. Awesome. So yeah, so here are some of the answers. If you want to check that out. Quick aside that we're gonna go into for this next slide. So we're going to look into a quick way to implement stochastic gradient descent in Python. But just to like break it down some more code beforehand, something in Python called list comprehension. It's a pretty cool way to manipulate lists and I guess arrays in a sense, or Python lists. And so basically, the syntax looks really weird right here. Wait. Not bad. Okay, cool. Sorry. My AirPods connected by for some reason. All right, cool. So going back here, we have this really funky syntax where we have array of I to the power of 2, but then we have a for loop right here. Now this looks really weird. This looks really weird because like, why would you have a for loop here and then like all that stuff, right? And so you could do this and it works, right? Basically what this is doing, we're taking this array right here, array. And so what it's doing basically is that we're gonna basically go from I equals 0 to I equals 4. So basically we're gonna go from like the whole length of the array. And then we're gonna make a new array called squared array, where basically the ith element gets turned into whatever this element is squared. So basically we'll get 1 squared, we'll get 1, we'll square it, we'll put that into the new array. We'll get 2, we'll square it, put that in the new array, 3, 4, 5, etc. And so now as a result, we basically done a for loop and we basically created an array that would usually take a for loop in like a simple statement. And so to make it even easier, you can basically not even go through this like whole range length thing. And so you can actually access each data point, I guess, in an array this way. So for number in arrays, basically we're gonna have a number. We're gonna have like a variable called number. It'll point one by one to each of these values in the array, and then we'll square them and add that to a new array called squared array. And so again, we're gonna go to array of 1, which is num. We're gonna square num, which is 1 again, and we're gonna add to the array. We're gonna go to 2. We're gonna square 2, get 4, 3, 9, yes, etc. And so basically, this allows us a really cool way to create new arrays in a really elegant syntax. And so that's how it works. You can do more things with it other than like what we saw here. So example down here could be like, I guess, doing this thing right here. Basically, we have a number and getting the individual digits of the number. And so we have a number that's called 249 82 305 09. Or I can't read the number, but you get the point. And so you have the number, we're turning it into a string, and we're going to get all the digits of that number in this way. So relatively helpful syntax, but for our case, what really matters is our stochastic gradient descent. And so right here we see that our I guess algorithm for that for this is going to take in our model, a number of epochs to train for, training data, a batch size, and a learning rate. And so, as we discussed before, we're going to train for a certain number of epochs. So we're going to have a range here. And so basically, we're going to train. We're going to loop for each epoch we have. We're going to shuffle the data, so basically mix it up so we don't get the same data at the front every time. And so then what we're going to do is we are going to basically create our batches. And so the big thing here is that, as you see here, this is where our list comprehension syntax comes into play. And so we have a complicated one here, but let's break it down. And so starting with the for loop, we have for I in range 0, length training data, batch size. And so what this is doing right here is basically we're saying we're going to start at 0, and we're going to go up to, but not including, the length of our training data. And then we're going to skip by batch size every time. So if batch size was 5, for example, we start at 0, then we go to 5, then 10, then 15 onwards. And so that's what this is. It's going on to the part that creates the array. What we're doing here is we're actually indexing into our training data. And we're basically taking one batch out of our data set. So you can see this basically as saying, like, for example, our first batch is going to be training data 0 until training data 5. So that's 5 data points, and that's going to be our first batch. Our second one's going to be from training data 5 to training data number 10. And so that's another 5 points, onwards and onwards. And so basically, we're creating these tiny lists of batch size data points, so we can put them in like a bigger list. And so now we have all our batches, and then we're going to train on all those batches. Any questions about the code or about the process of doing this? So my chat disappeared. That's fine, chat. Okay. Any questions about this code? All right, cool. Let us move on to another cool concept called dropout. And so the way dropout works is basically, while we're training, we're going to randomly kill nodes. So you can see down here, basically, our standard neural net looks like this. We have all of our nodes going in, like feeding into each other and stuff. But the way dropout works is that we're going to randomly kill, or basically zero out, some of these nodes. So you can see down here, these nodes get x'd out, and thus, because they have a value of 0, they don't contribute to the training at that point because they have a value of 0. It's not used during testing phase. And so the reason why we have this is for a thing called overfitting. We discussed it a bit last time. Basically, overfitting is a problem with training neural networks where basically your model, like, instead of generalizing to a big data set, basically memorizes the features of the data you trained on. And so as a result, you can't like generalize to broad features, but you only like memorize certain like things in your data set, for example. And so as a result, your model won't be good in the real world. That's, I guess, a way of saying it. And so what dropout does is basically, by killing some of these nodes, we're basically preventing the model from over relying on some of these nodes for its predictions. So for example, if like this last node over here was like had a really big weight to like the final output node, we could have a situation where we overfit based on whatever this node thought. And so thanks to dropout, we could have like a training step where basically this node is zeroed out. And so since it has no impact in this training step, the other nodes will be compensated and trained to compensate for the 0 node. And so we won't over rely on one node. And so in general, it works best in fully connected nodes, as we talked about here. It's kind of weird in convolution, so we won't get into it, but there's a paper there if you want to look into it. All right, I'll pass it on to Preetham for this next section.
All right, so we'll cover a short history of convolutional neural networks today. So I remember there being one person asking about dropout regularization in convolutional neural networks last time. We've covered dropout regularization. We'll just kind of revamp that convolutional neural network, namely Alexnet, and look at some more other neural networks that people have built. So first of all, we have convolutional layers and Rayleigh. So where do we get both of these concepts? So we got convolutional layers from a 1998 paper, which introduced DelayNet 5, and also the basic architecture of a convolutional neural network. So the convolutional layer, namely convolutions in that layer, and pooling were introduced. So we looked at average pooling and max pooling last time. So this time we'll also go over those things. And for Alexnet, we have Rayleigh. So Rayleigh was important in how we built convolutional neural networks in general. And we kind of saw that in a big picture last time. And more filters and having it deeper was also introduced in Alexnet. Alexnet became way more famous than LayNet, and it's also really popular for the industrial models today. So looking back at convolutional layers in Rayleigh, we looked at how there was a filter moving by a certain step size last time, and how the pooling layers were max or average. So for example, a filter moving past this 3x3 block would take the average of each of these, and then you'd get a convolved feature or something that would result from each step. So we talked about how max was better than average pooling last time because it highlighted the features that were better per se. And we also talked about Rayleigh activation. So this is just a quick review of whatever we talked about last time. So we'll move on. Oh yeah, so whenever you have any questions about whatever we talked about. Okay, so this is again review. So the pooling layers were max versus average. So if you remember the line going through and how there were two examples where one was more advantageous than the other. So we would have max pooling, where the I think it was like a black line on a white background, did better if it was the average pooling, whereas the max pooling did better on the other example. So we kind of looked at both of these, and we kind of came to the conclusion that max pooling was better than the other pooling technique, but both do have their shortcomings. So we need to address that as well. So the max pooling had a shortcoming with the lighter image part, and average pooling had a shortcoming if it had a darker background. All right, so this is just the pooling. Okay, so now the convolutional layers part and Rayleigh. So we have the convolutional layers, and so why Rayleigh? So we talked about Rayleigh as taking care of the vanishing gradient problem and increasing the gradient, so we don't run into that problem while we're training our convolutional neural network as we pass from layer to layer of the neural network. And we also talked about Rayleigh being more computationally better than our vanilla CNN without a Rayleigh. So that's the advantage of Rayleigh. So this is just a quick review again. All right, so Alexnet. So Alexnet is a popular convolutional neural network, CNN, and it's also one of the more prominently used and prominently developed upon CNNs in the industry. So we'll be covering that. Again, this is review, like this particular CNN's review. So I'll just go over this quicker. But again, if you have any questions, you could ask about it. So it was designed by Alex Krzyzewski, and this was in the paper titled Image Classification with Deep Convolutional Neural Networks. So if you want to look at that, you can. So we kind of said that, and it has been cited over 80,000 times. So just, you can see how popular that is. So go on. All right, so Alexnet structure. So one person did ask about the structure last time. So specifically, if it was dropout regularization and why it's applied before each of the first two fully connected layers. So last time we were like, wait, and we'll cover this in this lecture. So if any of you had the same question as that person last time, we'll address it right now. So dropout regularization, so as we discussed, chooses particular nodes in a layer of the neural network, and it chooses which ones to drop out for a particular training instance. So for example, you can make it random. So in a different training iteration, it would drop out different nodes and it would reduce overfitting. So why is that important? Because if it reduces overfitting, the CNN is more capable of predicting features like translation on the image and other things like that. So let's also cover the other parts of the architecture. So we covered convolutional layers. So it has 5 convolutional layers and 3 fully connected layers. So that was covered. Rayleigh is applied after each convolutional / fully connected layer. Again, to minimize that vanishing gradient problem and also to make the CNN faster, and max pooling to also reduce the computation, and also to make it so that your output image was scaled right and not like scaling so that we lose any features for the original image. All right, so GoogleNet and the Inception model. So this is where we start talking about models that we did not cover. So, yep. All right, GoogleNet / Inception. So this was the winner of ILSVRC 2014, which was a competition on developing CNNs. So it introduces Inception module. So we'll kind of talk about this, I think, later on. And what this is, briefly, like a high level picture, is it's a network inside of a network, kind of like Russian dolls. And we also have parallel filters with different sizes to detect varying size features. So before we had a fixed filter size. So this fixed n for n by n filters. So now we're going to see different size filters to detect features of different sizes. All right, so Inception, so feature size. So before we go on, I'm just gonna shout out to all of us who gathered pictures of dogs. So you could kind of, I don't know, take a short break and look at these. But we're gonna also try covering the rest of this workshop. So problem with the feature size was that the size of feature can vary from image to image. So if you can look at all these pictures of dogs, you can see that they're like, for example, different size ears, like for different breeds, or different like backgrounds, and like a certain feature that we don't define as feature, but the CNN can see. So these are all examples. So all right, so Inception and feature size. So what we're gonna talk about is convolution. So the filter concatenation. And so remember how we talked about there being different filter sizes and they're running all in parallel. So we have 1 by 1 convolutions, 3 by 3 convolutions, 5 by 5 convolutions. So previously we only had like 3 by 3 or 5 by 5 or 1 by 1, but here you can see that this previous layer has is directed to different sized convolutions. Maybe the 1x1 convolution detects some feature which is smaller, and then the 3x3, and so on and so forth. So this is kind of the Inception module and one of the main attributes to it and why it's better. So, all right. So again, this is just kind of the size of each of these data points as it goes from layer to layer. Yeah. And why is this important? So 1x1 convolution. So we talked about it here. We decided to put this because I feel like we introduced it, but we didn't really go too far into it. So let's just go over that. So 1x1 convolution. So what they do is they reduce your dimensions. And why is this? 5x5 and 3x3 are expensive if the depth and the input volume is large. So remember how we went over different varying feature sizes. So if we have a larger kernel for a larger feature size, it could be expensive. And we might as well use a smaller convolution to take care of that. And one example would be if the previous layer had a volume with depth 256 and the current layer has 5x5 with 250 kernels, then there's a huge amount of total weights. So that could be helpful. And so let's talk about how we would do this. All right, so okay, so how we would do this: one column to one voxel of the output. So a voxel is just this 1x1 filter size, and is just a, like, I don't know, a word that we put in because it's common, but we don't use it too much, but we wanted to expose people to it. And using this, we could compress the output depth and also preserve most of the information. So we don't want to lose the information for a feature like we do in polling. So we kind of have this thing to go along with it. So 256 depth and a 256 5x5 would have 1,638,400 weights. And similarly, if we did a similar calculation, we could get a 256 depth would go for 64 1x1 kernel, and then a 256 5x5 kernel, and we would have this many weights. So 425,984 weights. So it's a much better weight count than before. So we effectively compress this output. All right, so Inception Version 2 with the 1x1 convolution. So we looked at how a two-layer, or I don't know if we would call it two-layer, but two sets of convolutions stacked on top of each other, like in this diagram, would have a lower output size than for weights than if we just had only one. So if we had only 1x1 convolutions and filter concatenation, it would be worse than if we had 1x1 convolutions than 3x3 convolutions. And also a small correction, this could be better, but the 1x1 convolutions could be better. But if it were like 3x3, similarly compared to 1x1 then 3x3, then the 1x1 and 3x3 would be a better compression of the depth without losing properties of a particular feature. All right. Yeah, so this is just kind of showing how this could be better. Yeah. And our other model, I think this one would be the last but one model that we're going to cover today. It's Resnet, and it gave rise to residual layers. So we're going to also discuss what that is. All right, so Resnet, like I said, also won a similar competition just the year after GoogleNet did, and it introduced residual layers. So what are those? So we'll kind of cover that. So on a higher level, it's having the network learn a residual additive to the input instead of a raw transformation. So instead of this, in a feed-forward neural network, we would have a residual additive to the input. I think we're gonna show an example of that. All right. Okay, so why is it that we're gonna use the ResNet instead of previous CNNs? So previously we saw that deeper networks have achieved better performance. So I don't know if you remember, but I think in our beginning workshops of this quarter, we showed that compared to the logistic regression model with a vanilla neural network and a deeper neural network model, the deeper one performs better through an animation. I don't know if you remember, but so in short, they achieve better performance. But we also run into this degradation problem. So basically, it could be bad because it could also overfit the model as well. So that's kind of that. And the residual block. So why resonance actually became popular were the addition of a residual layer as well as performing better the previous iteration of CNNs. So a experimental question, but suppose we took a more shallow neural network and add additional layers to increase depth. So if we train this model, would it perform the same, better, or worse? So that's kind of a crux that the residual neural network kind of looked at compared to other neural networks and kind of evaluated this question, whether these neural networks perform better. And it was true that they perform better, but there's also quite a bound that we also have to account for without overfitting a certain model or having the so-called degradation model where our training error is quite high. All right, so in theory, it should perform at least as well as the shallow network. So we looked back and we saw that I saw that it would probably perform better. So we would have greater than or equal to performance. And it's because the additional layer could add weights that make it the identity function. So it could make it better than learning a zero mapping, which takes out a feature. So mostly in practice, the extra layers have trouble learning an identity mapping. So it's much better to, and a much easier time learning the zero mapping. So it's better for us to use a smaller amount of layers to avoid some problems such as like the degradation problem as we talked about. So what that was is, I don't think I covered it, but it was the training error doing a lot worse than the test error if we add far too many layers because of this issue. All right, so how do we get a identity mapping instead of a zero mapping? So we would use the solution of skipping or having residual connections. So instead of having the weight layers and going to Rayleigh this way, we would instead skip that and go to Rayleigh from our first part, our X, and that would be our identity. So remember how we said extra layers could have a vanishing gradient? So that could potentially be solved if we just went to ReLU instead of adding too many extra layers. And the name of the residual block comes from the extra x that is added to f of x. So that's also worth noting. All right, so if our weights went to 0, so basically if we avoided these weight layers, then the layer becomes the identity mapping, and that's kind of what we need instead of having a 0 mapping, which gets rid of some features or gets rid of some attributes of the feature. All right, so I'm going to be handing it off to Angeline to speak about the next part.
All right, perfect. So now we're going to go into a couple of like newer concepts on the next page. Okay, perfect. So right now we've just been really talking about classification using our CNNs, right? So classification, as the name just kind of suggests, classifies like what the image is, like what the image is of. Like, is it a cat or a dog or just a boat? So essentially its main goal is simply just to label an image. However, if we take it a step further, then we have detection and localization. So here, instead of just classifying like, oh yeah, this like entire image is just a dog, now we're kind of able to kind of pinpoint the location or like the general area of where like this dog might be. So essentially detection and localization is where we're kind of like labeling regions and attributing those regions to specific classes, like a dog class, or maybe like a class for leaves and stuff. So that's pretty good. However, we can do better. And this is where segmentation comes in. So segmentation is a lot like detection and localization in where it's able to kind of like locate objects. But what sets it apart from detection and localization is that segmentation is able to kind of identify every single pixel. And it's able to kind of like segment exactly where the class is. So let's say that we're looking for maybe like an image of like a dog on like a rock, right? So segmentation is going to be able to tell us that like this particular pixel is going to belong in the dog class, while the other pixels will like belong in like the rock class. So those are like 3 different levels, and yeah. Oh yeah, so here is kind of like a more visual, I guess, like diagram of like what each of the 3 different like levels of classification that we can get. So in the first one, we have like just a general image, like, yeah, it's a dog, And then in the second one, we're able to kind of like localize exactly where the dog is. And then in the third one, we're actually able to kind of like trace the pixels on like which pixels belong to the dog and which pixels are like not part of the dog. Alrighty, so within segmentation, we actually have 2 different types. So when we have like regular semantic segmentation, it's great because we are actually able to label the class of like each pixel, right? So you can see in the image to the left, we have our like 3 puffins that are just chilling on some rocks, and they're just like, enjoying their life. And when we have say regular semantic segmentation, we're able to identify that like, oh, these like 3 little birds here are actually puffins. But if you can kind of like look at the image, the computer is only able to identify that those puffins are puffins, but it's not able to distinguish like that this is like a puffin and the other one is like a different puffin. So with regular semantic segmentation, even though you're able to kind of like figure out like where the class is, you're not really able to distinguish between specific instances of the class. So this brings us into instance segmentation. And this essentially just solves like the drawback or the problem that we had introduced in regular semantic segmentation. So essentially, instance segmentation is just able to distinguish between multiple class instances within like the same class. So as you can see in the image below, now we're actually able to kind of figure out like, oh, this is like puffin 1, this is puffin 2, and this is puffin 3. And so this is like really important because like, let's say you have like an application for, like facial recognition. and you're trying to find so let's say like Bob's face out of like a layout of like 10 faces. You don't want to like have all the faces be labeled Bob, right? Because they're all faces. So when you have like instant segmentation, you're actually able to kind of distinguish that like, oh, this is Bob. This one is probably like Robert, and like that one is like Mandy. So this is why like this is very important. Yeah, okay, essentially, so like this is just kind of like going over like the general like ideas of like segmentation and like exactly how do we kind of like evaluate like the metrics. So I guess the first thing that we really do ask is like, what do the predictions and labels look like? And then how do we incorporate the predictions and the label to check if the model is performing well? And then so in order to kind of answer these questions, we can look at the AQI, which will help us kind of like figure these things out. All right, and then so for actually like implementing the segmentation itself, we are going to be talking very briefly about a different type of like CNN architecture, which is called UNet. And so as you can see, the reason why it's called UNet, because like this architecture very much looks like a U. And although this definitely does kind of like look pretty intimidating, you guys already do know pretty much all of the concepts that you need to know in order to understand this architecture. So essentially, so the downward sloping part of the UNet architecture is essentially just kind of like a very basic like CNN that we've been going through, you know, what, where you feed the computer the input, and then it goes through like the convolutional layers, max pooling, and all the way down to the very bottom of the diagram. And so at that point, we kind of already have like the classification model. So we're kind of like identifying like, oh, okay, this image is a dog, right? So essentially, when we just run like a normal CNN, we're pretty much halfway there. And so what the UNet will do is that it will take us from that halfway point and it will bring us all the way to the point where we want, which is like segmentation. And in order to do that, we actually kind of have to, in a way, undo some of the steps that we did during like the convolutional layers, as well as like the max pooling layers. Because if you realize every single time we apply like a max pooling layer, the image shrinks, right? And so by the time we get to like the very bottom of the UNet architecture, the image is extremely small and it has been like compressed into like this very like dense like container, right? And then so with segmentation, because our goal is to label pixels and to kind of like understand exactly which pixels from the input layer are like actually part of certain classes, it doesn't really make sense for us to kind of be dealing with such like a compressed image. So the goal of like the other part of the UNet architecture is to really expand these images back to kind of their original size. So then we can actually, you know, like compare the pixels with each other and figure out exactly which pixel belongs with which class. Okay, and then so I guess this kind of raises the question of like, now that we've downsampled everything, how exactly do we kind of like re-enlarge the image? Like, how do we like upsample, if you may? So this is where we kind of introduce the topic of transposed convolution. So transposed convolution essentially will kind of like undo some of the things that we did with like the max pooling layer or like the convolutional like layer. And so essentially the goal is to allow us to upscale the latent space, and we can kind of see on the next slide. All right, so this is just kind of like a diagram of like how like a transposed convolution can kind of like upscale our image and give us like a bigger final output. So as you can see, let's say that our input is this 2x2 like feature map over here. And so essentially, this is very similar to a CNN where we're going to run a kernel or like a filter over our input layer. However, instead of it causing the final feature map to shrink in size, we are actually going to get a final result that is much larger than our original input. So as you can see, since there's like a lot going around this image, let's try to like break it down to see like what's going on. So essentially, let's look at the input diagram at the very top left corner where you see the 1, right? And so when we run the kernel, this entire kernel over the 1, we get that. So we do like element-wise multiplication. So it's going to be 1 times 2, 1 times 6, 1 times 5, and like so on, right? And then essentially you place that the final outputs of like your element-wise multiplication into kind of like this new feature map, but you place all of the outputs from that one specific area into like the top left corner. So because your input like section was in the top left corner, the output section should also be in the top left corner. And then essentially you kind of do the same thing for every single part of the input. So if we go to like the top right corner with the 2, we will once again just run the kernel over that specific part of the input layer, right? And just do element-wise multiplication one more time. And then we're going to put all of the outputs of that specific section into the matching section of the final results layer, right? So we have the top right corner, we do element-wise multiplication, and we put all the outputs in the top right corner. And so as you can see, if we kind of do that for all like of the specific sections in our input layer, our final result is essentially going to be a feature map that is going to have larger dimensions than the original input layer. So essentially the big takeaway from this slide is not that you guys need to like understand all the math or like exactly how do we get from like this kernel to the other kernel. The big takeaway is just that transposed convolution allows us to take an input and produce a final output that is larger in size, which is really important because when we upscale, we want our outputs every single time we upscale to be larger than our original input. And so how this applies to UNet is that essentially every single time we do like transposed convolution, we're getting our original like input layer to be slightly bigger until it is finally reach, you know, the original dimensions of our like original input like image. All right, perfect. And then another very important concept to, I guess, like units is like the idea of copy and crop. So if you guys kind of remember when we talked about like max pooling layers or like average pooling layers, we essentially only take a certain amount of information from each section and then we just kind of like disregard the rest, right? And when you're downscaling, that's perfectly fine because like you don't really need that information in order to meet your end goal. However, every single time that we upscale, right, we kind of like need to figure out how to regain some of the information that we lost from the max pooling. And so this is kind of where copy and crop comes in. So if we could go back to like the original UNet diagram, I think this one might kind of be easier to explain with that. So if you look at the very bottom section where it has like the 56 squared by like 1024, that section over here. So essentially what we're going to do is that we're going to take all of the information from the opposite side of the architecture and we're going to copy that information over into into the feature map that we're working with. And because we now have all the information that we need, we're able to kind of recover some of the information that we lost during like the max pooling. So if you like look at the diagram, so we kind of do the copy and crop throughout our process of upscaling. So when we upscale, we essentially do a transposed convolution, right? So that gives us a larger image. And then now that we have a larger image, we need to be able to fill in some of the gaps that we lost. And in order to do that, we use the copy and crop. And so like, as you can see, we kind of do it periodically until like the final output. And then, yeah, we get to where we need to be. Okay, perfect. So that is essentially UNets. That was just so you guys could kind of like be exposed to a different architecture, as well as like the idea of like semantic like segmentation and all that stuff. So now we're just going to go very briefly to cover some miscellaneous topics. So these topics are they're very important in machine learning. And if you guys do projects in the future, these are some tools that you guys could choose to use like once you like start setting up your own models. So the first topic that we're going to cover is transfer learning, and more specifically, the pre-training area. So essentially, when you're building a model, you could like build a very great model with like a lot of like layers and that stuff, right? However, your model is going to need to be trained in order to kind of get like the optimal weights and biases, right? And so while that sounds like fairly simple, some of these models that you create can be very, very time consuming, especially if they have like hundreds of hyperparameters or maybe like 30 layers, you know? And so being like having to train those models is going to require a lot of time, but it's also going to require a lot of data. And so essentially what transfer learning does, especially with pre-training, is that it allows us to kind of like cut down on like the amount of time as well as data that we might need in our models by using a model that was pre-trained on a different data set. So essentially, let's say if I'm trying to create a model that is able to, you know, classify dogs, right? So instead of creating a model from scratch, you know, and training all the weights and stuff, I can essentially just kind of like take a model that somebody has created that is able to classify, let's say like cats, right? And use their weights and biases as well as like their architecture as like a starting point for my own model that would be like training on dogs. So that's essentially what this like pre-training part is for. So while it's able to like cut down on time as well as reduce the amount of data that I need, because you know the other person has already used data to like train it, one of the drawbacks is that you also have to make sure that your model and the pre-trained model is like similar enough to where the data is able to like transfer over. So like, let's say if I wanted to like classify dogs and the other person is like classifying like planets, you know, because like the features are very different. It might not work as well as if I were to choose like a model that was like trained on like a different animal. That's essentially kind of like one of the drawbacks of transfer learning like in pre-training. All right, and then some other, so essentially just a quick like overview of like the methods of transfer learning. So we went over pre-training and fine-tuning, essentially where you just kind of train one model on a data set, right? And then you just kind of take that model and then you change the classifier and then you just fine-tune that model to your specific classifier. So essentially just to reiterate like the dog example, so if I wanted to train a model on like a dog, right? So I would essentially just take like the cat model and then I would be able to like fine tune some of the final weights so that it would also be able to work on, you know, the dog model. And then another method would be freezing layers. So this essentially is where you take the trained model and you only decide to like retrain very specific layers, usually the final layers on the new data set. And so the great thing about freezing layers is that when you freeze the layers and you only need to train on the final layers, when you're training, the time that it takes to train is going to be greatly reduced because now you can kind of like breeze through the frozen layers and just really focus on like fine tuning and getting those like final layers very like specific towards your like end goal. Yeah, so those are pretty much like what transfer learning is, just like a quick overview. All right, so we covered quite a bit. So let's just kind of like take a little bit of time to just discuss things and maybe like refresh our memory a little bit. So I guess for like question one, What is the most notable advancement in CNNs made by Google's Inception model? Yeah, you guys can like talk about like the advancement or like what problem it was trying to address essentially. Okay, so essentially, the biggest like issue that like Google's Inception model was just trying to address was kind of like, you know, like the issue with like different feature sizes and like how do we kind of like adjust the model to be able to like handle that, right? And so it's able to kind of like create like a CNN that's a little more generalizable, which is like very important. And then I guess with like question two, like what is the mechanism behind like Google Net's like advancement? Yeah, perfect. Yeah, Daniel, you got it spot on, exactly. And so essentially like the biggest mechanism, as Daniel said, was just like the dimension reduction with the one by one convolutions. Yeah, perfect. Okay. And then question three, what problem do the residual blocks address in Resnet? Okay, so at least with ResNet, I guess like the biggest idea was that like ResNet was really able to kind of handle like the vanishing gradient problem with like the skip and yeah, just like it was really able to like solve like the vanishing gradient problem, which is just like the big takeaway of that model. And then I guess for number four, we only have two more left. What is like the purpose of like transposed convolution? Yeah, exactly. Perfect. Yeah. So essentially just the big idea of transposed convolution was just to kind of take like the input and then have the final output be of like larger dimension than the original input. Yeah, perfect. You guys got it. Okay. And then for the final question, what are the pros and cons of transfer learning? Yeah, you guys can just answer like only the pros or like only the cons if you guys want to. Yeah, perfect. Exactly. So you guys like hit on the pros very well. Yeah. So transfer learning is definitely faster. Yeah. Essentially, it just like speeds up the training, right? And then it also requires you to have less data when you are like dealing with your models. And just like one of like the general cons of transfer learning is that like sometimes you're not able to like transfer the knowledge very effectively if the two models that you're trying to like transfer between aren't exactly dealing with like a similar classification goal. So that's just like kind of something to watch out for if you guys ever want to use like transfer learning in the future. All right, perfect. You guys did very well in the discussion. Yeah, so here are like the discussion answers if you guys want to look over it on your own time. And then thank you all for coming. And then here's our anonymous feedback form. And then just to let you guys know, we do have like a couple events going on this week, I think on Wednesday. And then be sure to keep an eye out for the climate hack. Yeah, thank you guys for coming. All right, and if you guys have any questions, just feel free to like stay back.